Hi everyone, so in this video we are going to review another method of integration which is going to be useful for the models that we take a look at in class, and that is using a method called partial fraction decomposition. So where might this come up? Let's say we want to solve the following differential equation. dy dx is 8 times the quantity y squared minus 2y minus 3. So this is a separable differential equation. So if we want to solve this, we could divide both sides, for example, by y squared minus 2y minus 3. And at this stage, our terms have been separated. And so then we would integrate both sides. No problem integrating this. What do we do with this integral over here? We can't use substitution, won't work. Integration by parts won't work. We don't want to just integrate the denominator. And so this is where the method of partial fraction decomposition is going to be useful. So this method is entirely an algebraic problem. And after doing the algebra, then we'll do the calculus and integrate. Okay, so let's see how this goes. So the first step in this process is going to be, let's try and factor the denominator of this fraction, the bottom of the fraction, that we'll call the quotient q of y. So in this case, the quotient is y squared minus 2y minus 3, and we can factor that into y plus 1 and y minus 3. And then the next step is we are going to set up the following equation. And because our quadratic denominator factored into two unique linear factors, this equation is going to look like some undetermined constant a over y plus 1 is going to plus b over y minus 3 is going to equal 1 over y squared minus 2y minus 3. And so what is going on in this equation is we are trying to break up this initial fraction that we started with into two different fractions. So remember, if we started with this stuff over here, if I wanted to add two fractions with different denominators, we would put them over a common denominator. So what we're trying to find are what are the values a and b, so that when I add these two fractions together, I get back the fraction that we started with, which was the fraction inside the integral. So now step 3 is going to be, let's solve for these undetermined constants. In this case, we have 2 of them. In other cases, you may have more than just 2 undetermined constants. So that equation would look like, if I wanted to put these over a common denominator, the first fraction I multiply by y minus 3 over y minus 3, and the second one, y plus 1 over y plus 1. And now we've written this over a common denominator. So we've got a times y minus 3 plus b times y plus 1 all over this common denominator, y plus 1 times y minus 3. And this all should be equal to the right side that we started with, which had a numerator of 1 over this same denominator. So the only way these two fractions are going to equal each other is if the two numerators equal each other, because the denominators are the same. So distributing that a, we have a times y minus 3a plus b times y plus b. All of that should equal 1. So let's group our terms. We have two y terms, so that gives me y times a plus b, and then my constant terms are minus 3a plus b, and that should equal 0 y plus 1. And we need this 0 here to hold the place. So this is going to help identify the fact that we have two equations. One equation comes from a plus b should equal 0, and then we have a second equation which is going to allow us to match the constant terms on each side of this equation. So our first equation is a plus b is equal to 0, since we don't have any y terms on the right side of the equation. And the other one is minus 3a plus b is equal to 1. So we have a system of two linear equations in A and B. Different ways we can solve it using the elimination method. We could get minus 4a is equal to 1. So this tells me that a is equal to minus 1/4. And if a plus b is 0, then b must have the exact opposite sign of 1/4. And you can check that these values actually make this equation that we started over with true. And great, so now we've done the algebra part, and let's return back to the original question, which was, how can I integrate something like this? Now that we know how to break this fraction up, the key part is I can integrate this term, and I'm going to be able to integrate this term fairly directly. So let's see how this is going to work. So now we can rewrite this integral that we have up top as a, which was minus 1/4 over y plus 1, plus b, which was 1/4 over y minus 3 dy. So all I've done here is use this algebra that we were able to break this up. And now we can split up the sum of these two fractions and pull out the constant. So I've got minus 1/4 times the integral of y plus 1 plus 1/4 times the integral of 1 over y minus 3. And each of these we can integrate. I will skip most of the details, but you could integrate this one, for example, using substitution with y plus 1. And after doing this substitution and a similar one for the other integral, we would get minus 1/4 times the natural log of the absolute value of y plus 1 plus 1/4 times the natural log of y minus 3. And if we were just solving this integral, then we could have a plus c over here. So I didn't solve this entire differential equation. I'm just going to focus on how we would integrate the right side, integrating the left side over here. Integrating the right side, fairly simple, and we'll just leave it there. But what I really wanted to do was just review this process of integration using partial fraction decomposition. So I just want to summarize things on the last slide. Okay, so let's say we want to integrate a fraction, say that looks like p of x over q of x dx, such as the one, if I use x's instead of y's, that we had, which was x squared minus 2y minus 2x minus 3 dx. Okay, so that was equivalent to the integral we just looked at. So if I want to integrate fractions, here's a general process that we can try and go through. So at first, we can try and factor the denominator q of x into distinct linear terms. And that would give us, for example, the integral of 1 over x minus 3 times x plus 1 dx. So that was the first step that we took. And then for each factor, we get a term that looks like this. So if my denominator has two linear factors, then maybe it looks like this. If we have more factors, if q of x is a higher degree, maybe it's 3 or 4, then in theory, we could have more factors, and that means we would get a system of 3 equations with 3 unknowns and so on. If the denominator contains a repeated linear factor, so maybe I factor q of x and I get something that looks like 1 over x minus 2 squared, then when I do this partial fraction decomposition, we need to take into account that we could add fractions that look like a times x over x minus 2 plus b over x minus 2 squared. So if I add two fractions like that, the common denominator is still x minus 2. So I need to take into account repeated roots in a special way. And one other case would be, well, what happens? Not all quadratics can be factored into linear terms. So if we can't factor a quadratic, then instead of having one undetermined coefficient in the numerator, you can see over here, we have 2, ax plus b. So to generalize this, whatever the degree of the factor on the bottom is, on top, our generic looking expression should have 1 degree less. So if I have a quadratic down here, over here I have a linear numerator, ax plus b. And lastly, I just want to point out, if the degree of the numerator is greater than the degree of the denominator, then you may need to do polynomial division and then do partial fraction on the remainder. I do not think we're going to encounter any of these, but it's possible. So if you want to review this more carefully, look over the integration review materials. There are tons of examples and a bigger explanation about how this process works. All right, thank you everybody. See you soon.